Last time we mentioned that when you have an object that is submerged in a fluid, then an upward buoyant force is going to act on the object. And the how to calculate the buoyant force. Of course, this is the equation we use. That is Fb is equal to the mass of the fluid that's being displaced by the object. So this is Fg. So mf times g of course is gravity, and the m sub f is the mass of the fluid that's being displaced by the object. And of course, in fluid, we don't actually calculate the mass. We usually will like to use the density of the fluid. So the density of the fluid, and then times the uh, the volume the volume of the object that is in fluid. So I'm going to use V prime to indicate that this V prime may not be the total volume of the object, and then times G. So in other words, the mass of the fluid is the density of the fluid, and then times the object the volume of the object that's in the fluid. Okay, so so in this case, when you have, when you have, let's say, if you measure your weight in a fluid, then your actual weight and the weight in the fluid will be different because when you're in the fluid, you actually experience an upward buoyant force. So your weight in a fluid will actually be smaller than your weight in air. So so to write that in the equation, and the weight in the fluid, we call that apparent rate. So APP. So the apparent, sorry, this is so the apparent weight is the difference of your actual weight and the buoyant force. So we call that, let's say, WAPP, which is the apparent weight, and that's equal to your weight, let's say your weight in air, your actual weight, and then minus FB. So if you apply this concept, then it'll be easy to deduce the density. Take for example, to deduce the density of gold as the take-home quiz. Basically, you want to utilize this concept. That is the actual weight. The difference between the actual weight and the weight in a fluid is the outward buoyant force. And then outward buoyant force can be calculated using this equation. So that tying all together. So that concludes the Archimedes principle. And there are two more concepts from chapter 14 that students should be aware of. One is what we call the continuity equation. So what is continuity equation? Basically, the continuity equation is another way of saying that mass is conserved. So continuity. So continuity equation. Okay. So let's say we have a scenario like this. You have a channel. So this is a channel, and then the channel has a different cross-section area. So let's say at this side, on the right-hand side, it becomes smaller. So you have fluid that's flowing from the left, and let's say this cross-section area has the area A1, and the fluid is moving at a velocity v1. So this little v is the velocity, okay, that's flowing from the left and it's going out from the right. So in this case, let's say the area, we definitely see that cross-section area in this case, that's A2, which is different from your A1, and let's say it's moving at a velocity v2. So because mass is conserved, and we all know that, so let's say in the time delta t, then the same volume of the fluid enters from the left should be equal to the same volume of the fluid that's coming from the right. So in other words, if this is the amount of water, let's say the fluid is water, if this is the amount of water that this is a bad drawing. So during this time interval delta t, this is the amount of water that's flowing from the left. Then the same amount of water, same volume of the water has to leave out, leave from the right within the same time interval delta t. So in other words, how do we calculate volume? Basically, based on what we have here, the volume of water is the area. So you have the area on the left, you have the cross-sectional area, and then times the distance or the thickness. So you have the velocity times time. This will give you the distance that the water, the fluid has traveled, and then times the area. Then that gives you the volume. So the volume, because the fluid is incompressible, so the volume on the left must be equal to the volume on the right. So how to calculate the volume on the right? That'll be the cross-sectional area and then times the velocity. The velocity now is v2 and then times time your delta t. Okay? So in other words, area times the distance gives you the volume. How do you account for the distance? The distance will be velocity times time. So if you look at this within the same time interval, this go away, this go away. So in this case, what's left is that you have a cross-sectional area A1 and then times B1 that must be equal to the cross-sectional area A2 and then times the velocity V2. Okay, so that deduces a simple equation, which is based on the conservation of energy. This is what we call the continuity equation. Okay, because mass is conserved. So this equation basically tells you that if the cross-sectional area, let's say A1 is larger, if A1 is larger, then V1 has to be smaller, such that the product will stays, such that the product will stays the same when you have the smaller area times the larger velocity on the right. So the larger the area, the slower the fluid flows. Okay, so that's one thing, and that is the continuity equation. So the simple concept, and basically, is that you experience it every day. You see the water coming from a large area basically flows slower when the water going through, a bottleneck. Then it moves at a faster speed. Okay. Now the last concept from this chapter is the conservation of energy conserved by the fluid. In other words, that's a conservation. The concept of conservation of energy applies to fluids, and this equation, this equation is what we call the Bernoulli's equation. So Bernoulli. So what is Bernoulli's equation? So let's say we have a scenario like this. You have a channel. So the channel goes like this. It goes from, let's say, from this, and then the channel has changes cross-sectional area. And let's say that this channel is above some reference line. So this is, let's say, this is our reference. This is our ground. So when you have, let's say you have fluids that's coming from the left, and it's moving at a velocity v1, and let's say the cross-sectional area here is a1, and let's say it is at a height counting from the center to the reference point. Let's say at a height of y1, and also the pressure on the left-hand side is, let's say, P1. So these are the quantity. Okay, so in other words, you have a fluid that's going through a channel, and that channel is some distance like y1 above the ground, and it's moving at a velocity v1 through a cross-sectional area a1, and the pressure on the left is p1. And then this fluid is going to flow through this channel and coming from this side. So when it's coming at this side, it is at a distance that say is Y2 above the ground, and the cross-section area is A2, and the fluid is moving at a velocity V2. And on this side of the area, it experiences pressure, that's say P2. Okay, so based on the conservation energy, what we can, just based on this picture, what we can see here is that the pressure on the left, so you have your P1, and then plus your 1/2 density of the fluid, and then times the velocity through that through the cross-section area on the left square, and then plus the density of the fluid, and then times your G value, and then times the Y1, which is the locations of the fluid. That must be equal to the pressure on the right, and then plus 1/2 density of the fluid times velocity on the right square, and then plus the density of the fluid times G, and then times Y2. So this is the equation. This is what we call the Bernoulli's equation, and it actually is the it comes from the conservation of energy. So if we look at this equation closely, we can identify that if we multiply everything by volume, the first term is P times V. So if you recall, what is pressure times volume? Pressure times volume basically is the work. So this is this is like the pressure force does work. What about the second term? The second term you have, if you have 1/2 density times volume times velocity squared. When density times volume, that gives you mass. So we have 1/2 mv squared. So this is equivalent to kinetic energy. And the first one is work, because when you multiply every term by v, and the third term, when you multiply, you have density times volume, that gives you mass. So you have your mgh or mgy. So in this case, that gives you the potential energy. So you can see that this equation basically is based on the conservation energy. You have the work done by the pressure force. You have the kinetic energy of the fluid. You also have the gravitational potential energy of the fluid. Okay. So in this case, because energy has to be conserved, so every point on this channel has to satisfy this. So in other words, this equation tells you that the left hand side. So this equation basically further tells you that the whole thing here is a constant, and that is the Bernoulli's equation. Okay. Any questions so far? All right, good. So basically, we finished, officially finished chapter 14. These are the basic, the remaining, concept we didn't get to cover last time, but now it is, we finished that. So now we want to do two problems that apply the Bernoulli's equation. We will begin with the problem 58. So William, do you have your book in front of you? All right, good. So look at page 383. We're going to do problem 58. So while you read the problems, let me just do the drawing here. Okay, this is no, this is a very bad drawing. Hold on. Oh, that's okay. Let me just write down all the values here. So we have A1, that's 0.74 meter square, and we have B1, that is 0.4 meter per second. So that's on the left hand side. And on the right, we don't know the cross-sectional area. And the velocity is equal to 9.5 meter per second. Okay. And D here, the capital D here is 180 meters. And the density of water is 1,000 kilograms per meter cube. Okay, so what is this problem about? So this problem, we have the intake, which is on the left. The intake has cross-sectional area of 0.74 meters square and water flow at 0.4 meter per second. At the outlet, the distance D is 180 meters below the intake. The cross-sectional area is smaller than at the intake, and water flows out at 9.5 meters per second into the equipment. What is the pressure difference between the inlet and outlet? Okay, so basically we have, this is on the left is intake, and on the left that's outlet, and the separation, the height separation is 180 meters. We know that the cross-section area A1 is 0.74, B1 is that. So first of all, we don't know A2. Although it's not asked, it's not required. It didn't ask you to find out A2, but we can apply the continuity equation to figure out what the cross-section area on the right. So what we can do is just use A1 B1 is equal to A2 B2. In this case, when you plug in all the numbers, then you'll be able to figure out the A2 value. And so your A2 value, after you do the calculation, and that will give you 0.03 meter square. So this is simple. When if you're asked to find the cross-sectional area, you can just use the continuity equation. Now, what is the pressure difference? How do we figure out the pressure difference? Okay, so in this case, if we look at this, we can say that, okay, on the left we define everything in terms of with the index of 1, and on the right we define everything using the index 2. So if we recall the Bernoulli's equation says that P1 pressure plus 1/2 rho v squared plus rho gh has to be equal to the pressure plus the 1/2 rho v squared plus rho gh at any other points on the same channel. So in this case, if we define this as pressure P1, if we define this as pressure at P2, so in this case, you have pressure, you have your rho, you have the velocity, and then you have to define your height. So in this case, if we define our y1 here, if we define our y1 here to be your d, which is 180 meters, then your y2 is 0 because this is close to the ground, so we can define our coordinate system like this. So in this case, we are able to, just give me a second, I want to erase this. I'm not sure how to erase this. Okay. Oh, okay. So if we do this, so let me just write it here. So you have your P1 and then plus 1/2, P1 we don't know, and then plus 1/2 the density of the fluid, and then times the velocity, which is V1 square, and then plus the rho GH. So you have your rho, you have your G, and you have your H, and then Y. So you have your Y1 here. And that must be equal to pressure on the outlet. So that's your P2, and then plus 1/2 density of the fluid, and then times V2 square, and then plus rho, and then G, and then your Y2. So you can see that you have your P1 plus 1/2 rho, you have your rho and V1 and V2, they are all given. Your Y1 and Y2, they are also given. So so why don't you calculate what the density difference? I say you calculate this to figure out what the P2, what is P2 minus P1. So I'll give you 3 minutes to plug in the numbers and see if you can get the answer. Just type in your answer to the yeah, once you have the answer. So you're going to get a pretty large number. Whenever you're dealing with pressure, usually the number is pretty large because if you remember, one atmospheric pressure is 1.01 times 10 to the fifth Pascal. So usually you will get a huge number. So do we have an answer? Oh, you're still working on it. Okay. So while you're working, let me just turn to the next page, and then I'm going to put in the numbers. Okay, let me see. So yeah, that's correct. So P2 minus P1, that is, hold on. You might have missed, let's see, because this is what I got. I think there are terms that you might have, you may not have considered, so that you got a larger pressure. Let's see, the difference is about 4,000. So what would that be? 4,000. Maybe you forgot about this term. 5,000. 5,000 times. Let me see. This is 500 times. Yeah. Anyway, so whenever you do this kind of problem, the most common mistake would be that student define the wrong coordinate system, or they have the putting the negative 9.8 instead of 9.8, and also because you're dealing with huge numbers, students sometimes they will calculate wrong. So let's look at this equation. You have the P1 plus 1 half rho V1 squared plus rho G Y1. That's equal to P2 plus 1 half rho V squared plus rho G Y2. So we don't know P1. We assume that, and then we plug in whatever we are given. So you have 1 half times 1,000, which is the density of the fluid, and then times the velocity. And remember to square it, because a lot of times students have that, but they forgot to square it when they calculate it. So we have the V1, which is zero point 0.4 square, and then plus 1,000 times 9.8. And because we define Y1 to be 180, so you have 180 on the left-hand side of the equation. Now on the right-hand side of the equation, you have your P2, and it plus 1 half thousand times 9.5 square, and then plus 1,000 times 9.8, and your Y2, because your Y2 is defined as a reference line, so it's 0. So after you rearrange you calculate numerical values, rearrange that, you find out the pressure difference between the outlet and the intake is, this is a huge number, let's see, is 1718955 Pascal. Okay. All right. So that's one problem that it's better that students know how to do that. Now we're going to do another problem, which is 61. Any question, William, before we move on to problem 61? Okay, so let's do problem 61. I'm going to turn to the next page. Okay, problem 61. A water pipe having a 2.5 centimeters inside diameter carries water into the basement of a house at a speed of 0.9 meter per second and a pressure of 170 kilopascal. If the pipe tapers to 1.2 centimeters and rises to the second floor 7.6 meters above the input points, what are the speed and water pressure at the second floor? So when you read the problem, you want to also draw the diagram so that you can define your coordinates. And so what we have here is that you have the ground floor that go to the second floor, so something like this. So this is your all the index that's your 1, all the this is your 0.2. Okay, so your because we define this the h1 here or y1 is 0. So in this case, the second floor, the y2 is 7.6 meter above the input points, and the diameter of the channel is given, not the area. So in order to figure out how fast the water, is flowing at point 2, when the velocity at point 1 is given, we want to use the continuity equation. And the continuity equation says that you have your A1 times V1 has to be equal to A2 times V2. So how do we calculate the cross-sectional area of this at point 1 and at point 2? So whenever you have cross-section, you have the pipe like this, the cross-section area basically is a circle. So when you have a circle, the area of a circle, will, of course, will be just pi r squared. And you're given a diameter. So applying the A1, B1 on at the point A, so you have your at point 1, so you have your pi r squared. So you have your pi, and what is your r? Your r, of course, is your d1. So you have your d1, which is 2.5 divided by 2. That gives you r. And then remember, this is centimeters. So you want to convert it to meters. So times 10 to the negative 2, that gives the meter. Okay, so this is pi r, and then of course you have to square it. And then your v1 is 0.9. That's on the left-hand side of the equation. Now, on the right-hand side of the equation, you have your A2. So A2 will be pi, and then times the R squared. So you have your R, which is 1.2 divided by 2, and then times 10 to the negative 2. This is your R, and then you have square it. So you have your pi R squared, and then times your V2. So this is how you calculate your V2. So William, why don't you quickly calculate that and see what value that you get? So this kind of problem is, when you apply the continuity equation, it is easy to use, but sometimes there are still make mistake because when they do the calculation, they forgot to convert the unit, use the SI unit, or they just take the diameter as the area. When you're given the diameter, it's not the area, so you have to use the pi r squared to calculate the cross-sectional area. Okay. And so when you calculate this, you'll get the velocity at point 2 equals, after you do a calculation, you'll get 3.9 meter per second. And this tells you that when the cross-sectional area is smaller, the water flows faster, because now initially the velocity is 0.9. When it get to the cross-sectional area that has a smaller cross-sectional area, you can see that the velocity actually is larger. Okay, so that's your part A. Now, how do we calculate pressure at this point? So again, whenever you're asked to calculate pressure, you have to apply Bernoulli's equation. Okay, so Bernoulli's equation tells you that P1 plus 1 half rho V. Let me just write down. So you have your P1 plus 1/2 rho V1 squared plus rho GH 1, that must be equal to P2 plus 1/2 rho V2 squared and then plus rho GH2. So this is the equation. Now we just plug in the numbers. So your P1 is 170 kilopascal. Kilo is not a SI unit. You have to multiply it by 1,000. So you have 170 times 1,000, and that will be the pascal. And then plus 1/2. The density of the fluid is water is 1,000. That's for water. And the velocity is 0.9. You square it to remember that. And then plus your H1, so I'm not going to write down all that stuff because H1 is 0, so this is just 0, and that must be equal to the pressure at point 2, which we were asked to find, and then plus 1/2 density of the fluid, and then times the velocity at point 2, which is 3.9. Remember to square it, and then plus the density of the fluid, which is 1,000 times 9.8, and then times H2, and your H2 is 7.6. That's in meters. So after you do the calculation to rearrange that, you'll be able to figure out the P2. So the final answer, so your P2 is equal to A8, let's see, AA320 Pascal. So that's the pressure at point 2. 88,320 Pascal. Okay? Any question? Okay. So let me just draw a line here. Now, sometimes students get confused. When do you use, because when you're asked to find pressure, okay. When you're asked to find pressure, there are actually two equations that that deal with pressure. If you recall, last time in class we mentioned that the pressure on the fluid can be calculated, which is P2 is equal to P1, and then plus rho GH, and so this is, and then we also have the P plus 1/2 rho V squared plus rho GH. That is a constant. This is Bernoulli's equation. So what's the difference between these two? Okay, if you compare these two, the first one here is hydrostatic, when the water does not move. When you're dealing with Bernoulli's equation, this is when water actually, or the fluid actually moves. So when fluid moves, then you have this extra term, the kinetic energy, 1/2 rho v squared, that you have to take into account. So that's the difference between the equation that that is applicable only when you're dealing with a static situation, and when the fluid is actually moving, then you have to use the Bernoulli's equation. So this is just the I just want to point out that you do want to when you calculate the pressure, when do you use the Bernoulli's equation? This is when the fluid is moving. And when do you use the top one? This is basically is when you have, if you recall, this is the static situation. Let's say this is the interface. This is the interface between air and water of any fluid. If the pressure at this point, that's atmospheric pressure, or let's just say that's the pressure P1, and this is your pressure on the fluid, that's your P2, and the distance here is h, then your P1 is equal, your P2 is equal to pressure, and then plus rho gh. Okay, so this is, when you calculate pressure under the fluids, and this, but this equation is when you have fluid that's moving. All right. Any question? So that's the basic distinction between these two equations. Although both equations deal with pressure, but when you apply, you have to choose when to use which equation. It depends on whether the fluid is still or is moving. And if we don't have any questions, we basically finished this lecture. And of course, in class, come Tuesday, we're going to do a class demonstrations on the Archimedes principle, and do probably one or two more problems in class. And then we're going to move on. We're also going to cover the last chapter of the semester, which is chapter 17, the sound wave. All right, William, any questions? Okay, in fact, I'm going to stop the recording so that we don't waste time on